Oh, sorry, because of the delay. I had problems with my machine, what is basically a shame, because my intention was to show you a bot with this case, but it was linked to my machine. So after that, if anyone wants to see, I can show you in particular the images and things like that in real time. So let's go with a static presentation. Okay, so I'm Luis. I'm a physicist. I'm a physicist from Unicamp. Okay, I'm finishing my PhD there. And also, I'm a data scientist at Konker. And I will talk to you about a project that actually is starting now. So this is a work in progress, okay? So yeah, it's not finished, and we'll see that's not finished at all. But the thing that I want to show you is this collaboration we are doing with Smart Campus from Unicamp with Konker. And we have a student and a professor working, in this case, with us. They will probably next semester we'll have something much nicer to show you. This is just a work in progress. So the first thing is, Konker is an IoT startup. Okay, we are 5 people. We are a spin-off of a bigger company, but we are 5 people working on that. And the first thing that you'll probably ask is this: why? Why IoT talk at PAPIs? So I will try to convince you in the next 5 minutes that IoT and machine learning is a perfect match. Okay, so as I was talking, this is more a talk, more a recipe of what we are doing. So if you want to interact during the talk, please do. Okay, if you need to ask something, if it's not understandable, something that I say, please talk to me. There is no problem. I prefer that than questions in the end. It's easier. Okay, so why IoT on the machine learning conference? Okay, so just show. The idea is to show a little bit, try to convince you that Internet of Things and machine learning is a perfect match. Then problem definition, proposed solution, a demonstration that will be static, but okay. And after all, if you need questions about specific things, go ahead. But please do during the talk too. Okay, Internet of Things. The first thing that I want to talk to you is something that people usually say it's Internet of Things. When people start talking about Internet of Things, usually they say, oh, I have a device. Here it's just a lamp. So I want to simply turn on and off this device. So I use my mobile. And this is IoT. And that's not quite what we think about IoT. The idea of IoT that I want to pass for you right now is that you need to actually have a virtual device and a real device. A real device, not exactly, but you need to represent what you are doing as a virtual device, like people usually say today as digital twin or something like that. But more general, you want to do something that you do virtually, interact with something that you do physically. So this is the first level of IoT. You have a virtual device, you have a real device, you want then to interact with each other. So, okay. Next level of IoT, you have a virtual environment. So I have a field device. Here we could have a thermometer, air conditioner, a few lamps. And I have the same environment in a virtual place. So we have a virtual environment, and this virtual environment communicates with the real environment. This communication, it's whatever you want, actually. This is not important. The important thing, you need an environment, and you need a virtual environment and a real environment talking to each other. So most of the IoT projects right now are this kind of project. When you talk with about IoT with big enterprises like Google, like others, like Amazon, you talk about this kind of things. You have a device that controls the environment. So this is nice, this is okay, but this is second level IoT. What you are thinking about right now is the future, the third level of IoT. Sorry about this in Portuguese. I just noticed a few minutes ago that it was in Portuguese, but this means everything okay. So yeah. So the last level of IoT, at least for us, what we think about when we talk about IoT, is that you have everything sending data to the cloud, and the cloud itself takes the decisions. This sounds like, I don't know, a little bit crazy, a little bit apocalyptic to someone, but actually we are doing this kind of things, usually locally, for a long time. If you probably, you drove a car in the last few years, and probably you never notice, never think about how the engine works, or how you change the mixture of air and combustion, and fuel, or about the pressure of the oil. Usually the car makes the decision for you. You just need to go there, start the car, and go ahead. So we do that in small things, usually not connected. And the next level of IoT is do the same thing, but in the cloud, with a lot of, okay, sorry. So do that in the cloud with a lot of different data coming from different things. You can have the weather coming from a weather site. You can have things locally in your place, and the network, the cloud, actually take the decisions and send to you if everything is okay or not, just like that. So we believe this is the future of IoT. We truly believe this is the future of IoT. And for this makes sense, we develop an IoT platform. That's basically, we have now a IoT ecosystem. We try to communicate with everyone that has projects and try to integrate with the things that we do. But the backbone of all this is a platform that I'll show in the end with the data that we are sending. So we have a platform in the cloud. It receives data from a lot of different devices with a lot of different formats. And it's there that the magic works. Okay, so going back to the problem. Okay, where can I park my car? We see solutions about smart parking. Every time you go to a shopping mall or something like that, you probably see this kind of solution. We have a small device on the ceiling. It detects the car that is above it. So usually using ultrasound. And okay, this kind of works fine for closed environments, but this will never work fine in an open place. You have rain, you have a lot of problems with that, so you don't have a ceiling to put the device, you should put in the floor. And if you don't want cables around your parking lot, you need batteries and change batteries, and this is not a good solution. This works okay for closed environments, but for an open environment, it's not okay. So we thought about, why don't we use the images to do that? Kind of, it's an obvious solution. An image can take everything can take all the data you need to process from all the parking lot in one single image. So why not? The main problem with that is that you should not send the images of public place with people, usually, to the internet. And this is a problem even bigger if you send this to a cloud that's not in Brazil, that doesn't follow regulations. So this is kind of bad. And the only solution that we found for this is running the analysis directly on the place that you take the data. So okay, that's fine. That makes sense. But you need hardware to do that. So one solution that you could do is just to have a network, send this photo through the network to a server with a GPU and do everything that you want with deep learning on this GPU. But usually, you don't want to trafficate pictures over a network that's meant to IoT. IoT is meant to be a network with low bandwidth, with probably most of the time that's not working all the time, that has downtime, a higher downtime that you expect. So that's not a good solution too. So we will try to do something that is kind of interesting, that is using a Raspberry Pi Zero W to take the picture and to process the picture. This is the camera that we made. It's, yeah, I don't have here the picture. It's in my machine. I can show you later. of the place. This is at Unicamp, at the Computer Science Institute. And we run on this Raspberry Pi Zero W, the TensorFlow and the Debian environment. And okay, first thing that I need to say, it's a warning. If you do the same thing that we did, and you can use anything better than a Raspberry Pi Zero, like Raspberry Pi 3, use it. Okay? The problem is not only the memory or the clock of the component, it's the architecture. They use ARM v6 architecture, and it's quite complicated to compile everything you need here. So if you can use a P3, please use it. It will be easier for you. I can tell that. It took me, I don't know, a week to recompile everything that I need to do this. Okay. That said, okay, the first thing that you probably do when you need to solve this kind of thing is just to check what you have about, what models we have pre-trained on TensorFlow. The Coco model seems a nice fit because they have cores. So it's everything that you need. Okay, so this is from this page of the models of TensorFlow. You probably saw that a lot of times. And okay, we tried the first models, the mobile net models, and they didn't work well. Simply didn't work well at all. We had, out of the box, we have a result of around 20% of detection. So it's not good enough. After that, you have Inception. So as it was the next model, we trained the Inception using another framework, let's say, that we like at Konker, that is TensorBox. So we'll use TensorBox with Inception v1, that's Google the Net, and using this code for TensorBox. And I will show in a few slides, but we use Inception for creating the data set, okay? We didn't have time to create the data set by hand, doing the annotations. So I show you. So I use Inception to generate the first annotations that trained the network and so on, okay? So this kind of image that we have there, okay? This is 3 images. Of course, the images usually don't go away from the device, it stays itself. I just took 3 images to show you. So this is not the normal operation of the thing. We obviously need the images to train the network, but we can do that locally in the same network, so it's easy. Okay, so we took this 17,000, almost 18,000 images, and from just 13,000 from a single location because the camera fell down. Okay, so we need to replace the location of the camera. It just happens too when you need physical things. And about this data set, I selected 4,524 pictures. The selection is something funny that I'll show in the last slides of the presentation. But most of this data set was taken in January, February, so it was vacation on the university. So we had a few cars there. So I took a lot of pictures with no cars. Okay. So why the first thing that you usually do, you do the annotations if you are doing the training. So let's do something to accelerate the process. As I told you, I took the exception network from Deep Lab, and it runs on our image, and you can it gives us a beautiful mask of where we have cars. This mask is not really useful to locate each car because it's a blob, of course, but we can do something like this. We know where the parking spots are, so we can do by hand, create the box by hand, and then, okay, the resolution is not good, but okay. Anyway, so we took by hand the position, and then we test if we have superposition over the mask from Deep Lab exception, and or boxes. So I just put a threshold of 50% of interception, and then I create a data set saying what kind of things we have here. This kind. The result is this kind of data set. We have the file with the timestamp, and the data set says no car, 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 no car, car, car. Okay? So I saved this. This accelerates a lot the training process because it took the boring part of do the annotations by hand. And then what we do after that, we take the mean position of the cars. Literally, we just put one picture after another and create the mean position of the cars. And then I create a annotation for that and replicate using this data set. So now we have everything that we need to train the system, okay? And well, as I told you, this is not good enough, okay, for most of the things. I just did my validation tens of the pictures. It's not really a good process. So this is a work in progress. It's starting now. I actually accelerate the things to show you something more nicer than just a few slides about the method. So, okay, we use TensorBox to training. We trained it to 53 epochs. That sounds low, that sounds small training for this, but it's just the final layers. The TensorBox is already trained with the ImageNet dataset. So we just took the pooling layers basically and put the detection system, the SSD system there. So 53 epochs is more than enough. We had validation of 98% on there. And of course, it was going down. That's the best point we find. It's kind of difficult to evaluate directly the performance using the validation dataset because you have another threshold to select the cars. So we have the threshold of the confidence level of the system. You have another threshold that is the combination over the union. So it's kind of difficult to see if this is good enough just after the training. But after this 53 epochs, we were overfitting, so yeah, it should be enough. So what we have after that? Okay, yeah, I forgot. Another warning, especially for beginners, okay, on this. I don't know if the public, how is the level of the public, but when you have images that you take one after the other, this is not a Poissonian data set. We cannot simply put on the scikit-learn and say, okay, just put train and validation data set randomly. This will not work. This will not work. We will probably get a tremendous overfit on your system. Because the one picture after another, I don't know, imagine a movie. If you take 30 pictures a second, one picture after another, you have mostly zero delta entropy. The difference of entropy of each image is almost zero. So if you put one of these in training, another of these on the validation, you will overfit. So please, if you're doing this, just take periods of training, then period of validation, training and period of validation. Just a small tip to everyone that's starting this now. Okay, so, okay, this is the first result. Not very promising. Okay, so yeah, very bad. Anyway, after I filtered the data set a bit more, we took this. Okay, it's getting better. After changing the thresholds, we get this kind of thing. It's not good at all. But at least you can see the cars. Yeah. And after balancing the data set, we finally have something that works. This was the first image that really works. Okay, it was my car. It was empty, so I went there just to take a picture. Yeah. So okay. So another thing that's very important, it's to balance the data set. This kind of thing was happening because we had a lot of images with just these two cars, a lot. Because as I told you, they were in vacation, so probably the first person that enters just go there, and the second here, and that's all for all day. So it's a very important thing to balance the data set. So, okay. I will try to show you what's happening. So we have now the thing. We have the Raspberry Pi. the Raspberry Pi process the data and send to the platform. And for now, we're not doing anything with that. But the next step is to show that, to show people if they can go there and Spark or not. So let me just show you. Okay, this is the platform, the first screen. And then you have this. This is my section. I have a few devices here. This one is this. So if you see here, let's see if it's working now. The device. Okay, so this is what's happening. This is the message that the device is sending. Okay, count part is the channel that's sending. This is the spots. So occupied, free, occupied. Okay, so this is what's sent. What time is now? 10 minutes ago, more or less. It takes more or less 2 minutes to run that on the Raspberry Pi, just the TensorFlow network. So it sends this. I put 5 minutes, but the network's not so good. So sometimes it takes 10 minutes just to send the message. So it's more or less like that. So what you can see, I can show you after that a bot that do that in real time. But at least we can see how is this happening. Let's see. I don't know. Let's take Park 1. So this is what happened. So it was free. The second spot was free until 8 in the morning, and then it's occupied. It's not free anymore. So it's working. It's working. It's a work in progress. We don't have a visualization, a beautiful visualization for this, but this will probably probably will be done by the students. So Unicamp has a mobile app, so probably we'll integrate this kind of thing in the mobile app. And in this scenario especially, I wanted to show you something that it's not exactly a device sending data to the network, raw data to the network. We have actually who is sending this data to the IoT platform is the neural network. So our device is a neural network in this scenario. And this is the beauty of IoT. You can have anything send data, and this data can be analyzed, and you can take a lot more value of this data online. Okay, so yeah, that's all that. After that, if you want to see the in real time, I can show you my PC. Okay, okay, that's it. Okay, we have time for 2 questions. Okay, go on. A microphone. No. Okay.
Thank you. I'll make the question in English.
Oh.
I just want to know if we have to replicate this for other spots. How troublesome would be to create the masks and have the other image for other cameras or other positions?
That's a good question. Actually, we had a lot of experience with TensorBox to another problem that we solved. We're still solving, but we work on Konker. That is to detect things inside refrigerators. So we'll have, I don't know, an apple, we'll have a soda can, or something like that. So you detect things and count things inside the refrigerator. And after training with a few different heights of different refrigerators, we got a very good generalization. So I think if you do that for 3, maybe 4 different parking places, parking lots, you'll probably get a very good generalization over the course. Might work. Yeah, it probably work. And then you can have something even better. You can have a drone taking pictures from above and try to generalize that. That would be beautiful. Okay.
Hello. Nice presentation. Did you have problems with occlusion on your data?
Yes.
And did you test it with like windy situations or rainy situations?
Yes, actually, rainy situations was no problem at all because the camera is inside a small box that protects it very well about over rain, wind, and things like that. But occlusion, yes. every time that a truck stops at this parking lot, we have problems with occlusion. I took away that from the data set, from the training data set, but this will be a problem in the future. No, that's not a problem. That's not a problem. Let me show you. The camera has a protection for that. So we don't have flares on the camera. But I had another problem that was funny. Let me take a Raspberry Pi here. If you do that using this kind of case, for the Raspberry Pi Zero case, you might consider to put black ink here, just to put tape or something, just to make it black, because this causes on the glass reflection. So you always see the Raspberry Pi on the image. So yeah, you might consider it's a good idea to just put this black somehow. Okay, that's all. Okay, thank you.